This lecture begins our study of circuits. Circuits are paths for charges to flow. What do we mean by charge flowing? Well, we define a term called current. In equations, it's symbolized by the capital letter I. It is the charge per time passing a point in the circuit. In the little cartoon to the right, we see some charges traveling around a circular path, and we see a dotted line. As the charges pass that dotted line, that is what we mean by passing a point in the circuit. So current is a measure of how quickly or how many of these charges are passing that point in a given period of time. The unit of current is amps. 1 amp is equal to 1 coulomb per second. That is 6.25 to 10 to the 18th electrons per second. So for 1 amp of current going around a circuit, there would be quite a few electrons going around a circuit per second. Why would the electrons go around a circuit? Well, there's a quantity called voltage, which is a measure of the potential energy that drives the flow of charge in a circuit. Its units are volts. A circuit element called a battery is the source of constant voltage that typically drives the current in a circuit. And in a circuit diagram, it's symbolized by this symbol, this shown to the right. Resistance is a measure of how much a circuit element resists the flow of charge. The units of resistance are ohms. In an equation, resistance is usually symbolized by a capital R. The units, 1 ohm is equal to 1 volt per 1 amp. A resistor is a circuit element that has resistance, and it's symbolized by the jagged line to the right in a circuit. Ohm's law, V equals IR, relates these three quantities. If we have a resistor with a resistance R, shown by the blue jagged line, with a current I passing through it, then the voltage V1 on the left-hand side compared to the voltage V2 on the right-hand side are given by Ohm's law. So precisely, V1 minus V2 is equal to I times R. The power loss in a circuit is due to the resistance in the circuit. The resistance converts electrical energy to heat, just like friction converts kinetic energy to heat. The units of power loss are watts, and power is given in terms of the current times the voltage, or using Ohm's law, we can rewrite that in terms of current times resistance, or current squared times resistance, or voltage squared divided by resistance. It is common to use a water flow analogy, the flow of current for the flow of current in a circuit. So we look at how the flow of water is like the flow of water in a river. The resistance for water flow is determined by the width of the river and the things in the river. For example, you can have a thin or narrow river compared to a wider river, so that the wider river would pose less resistance than the narrow river. Or we could have a river that's filled with rocks, which would have a higher resistance than one that had no rocks. A thin wire, going back now to the flow of current, has more resistance than a thick wire. So like a narrow river has more resistance than a wide river. A wire made up of a good conductor like copper lets charges flow more freely than a bad conductor. So copper basically has fewer rocks in the river. Water tends to flow downhill because of the change in gravitational potential energy. Imagine a waterfall. Charge flows from high to low voltage because of the change in electrical potential energy. Here we show a little circuit which has a battery, and going from the minus to the positive side of the battery, there's a big step up in potential energy. So the current likes to flow from the positive side of the battery to the negative side of the battery.